Hello and welcome to the IRENA online seminar series. We are very excited to have Dr. Kaley Brauer as a speaker today. Dr. Brauer is an NSF Astronomy and Astrophysics postdoctoral fellow at Harvard University. Previously, she received her PhD from MIT. She specializes in early galaxy formation, stellar nucleosynthesis, and cosmological simulations. Her work focuses on modeling the chemical enrichment processes in the first galaxies and understanding observations of ultra-faint dwarf galaxies and metal-poor stars in the Milky Way. So we are very excited to hear from Dr. Brauer, and let's welcome her. So Dr. Brauer, you can start with the presentation. It's all yours. Take us away.
All right, thank you so much for that introduction, and thank you for having me. Today I will be talking about some work I did with these wonderful collaborators here on the screen. And this work is part of what we're calling the Aeos project. And as part of this project, we are simulating stellar chemical abundances and galaxy formation in the early universe. So we'll be seeing some more videos like in the background here in a second. But first, I wanted to get into some of the background here. So let's just start right at the beginning with a brief history of the universe. 13.7 billion years ago, there was the Big Bang. And following that time, there's a lot of hot, dense, expanding in the universe, but there was no stars yet. And so for a period of time, there's no stars. This was the Dark Ages, until the first stars started collapsing and forming a few 100 million years after the Big Bang. So this is still very early on in the universe. We start getting the first stars, which allowed us to get the first galaxies, which are just groups of stars and gas in different collapsed areas of the cosmic web. And one additional period right after this I want to point out is in the history of the universe is this period of time called reionization. This is when the ionizing radiation from the first stars and the first galaxies started ionizing all of the neutral hydrogen in the universe. And this is going to be important later. So I wanted to point out that this is all happening very early on in the universe. And then ever since then, it's been about 13 billion years. The universe has expanded. There's been more stars, more galaxies, and eventually we hit present day, which is of course where we are now with the Milky Way galaxy, which is our home, and a bunch of other little galaxies and the stars all around us today. So the first galaxies formed, as I just said, in the first billion years after the Big Bang, the first few 100 million years. And every galaxy that we see today, including our own home, the Milky Way, is a result of mergers that started with those very first galaxies and those very first stars. And I wanted to point out, this picture that I'm showing here is a very deep image from James Webb Space Telescope. And you're seeing tons of galaxies here. That's what all these little smudges and shapes are. But what you're not seeing in this image is actually any of the first galaxies. Those are beyond even the capabilities of JWST. So even though we're very interested in our, origins in the universe and how these first stars and galaxies formed, how all the chemical elements that make us up and make up our world came from, we can't see any of that with even the most advanced technology that we currently have, JWST, at least not directly. So that's why I'll be going into other ways that we're able to study the first galaxies. First, just very basic galaxy formation information is that the primary way galaxies grow is through mergers. This is a little visualization that obviously is not real. That's not how it actually looks, but it's the primary way that galaxies get bigger over time is by you start with a few little collapsed galaxies early on, and then they eat up each other. They get bigger and bigger over time. And this is an actual image, what it actually looks like. These are the mice galaxies as seen by Hubble. And a galaxy so this is one image that Hubble has seen of two galaxies that are merging, and they have all this structure and tidal tails. And a galaxy like the Milky Way, our own galaxy, has experienced dozens of mergers in the last 13 billion years to build us up over time. So the Milky Way today looks something like this if you look at it from the side. And just to kind of walk you through the different components, we have here in the middle, we have the bulge, which is a bunch of very old stars. We have the thin disk, which is where the spiral arms are located, where most of the ongoing star formation is, and is in fact where we are located, about 8 kiloparsecs from the center here. Around that, we have some more stars. This is the thick disk is kind of puffed up around the thin disk. And so in here is where most of the action currently happening in the galaxy is going on. But if you go farther out into what is called the stellar halo, there are a lot of very interesting old things. One of the things you can find in the stellar halo are dwarf galaxies, some of which are very ancient systems. You can find some globular clusters, which are these collections of stars. And you can even find just loose stars, just strewn about in the Milky Way. Some of them from these dwarf galaxies that merge into the Milky Way over time. And this is not fully to scale here, but all this is kept together in this dark matter halo that goes out to about 300 kiloparsecs. So that's the Milky Way as it is today. One question that myself and my collaborators are interested in is how exactly did the Milky Way form? And of course, I'll be talking particularly about like the chemical abundances in the Milky Way here in a little bit. But how exactly did all this form? And how can we study its history from the universe, early universe, until today, based on what we are able to see right now? So I'm going to be focusing on two portions of the Milky Way and trying to explain some of the work that we're doing to start trying to interpret how observations of these things to learn about the early universe. And that's going to be the dwarf galaxies that orbit around the Milky Way, and also some of the really metal poor stars, which are some of these very old stars that you can find in the stellar halo. So some of the smallest dwarf galaxies around the Milky Way today are actually relics of the very first galaxies. I'm showing here a picture of Reticulum 2, which is an ultra-faint dwarf galaxy that is orbiting around the Milky Way. And this is one of dozens of small, faint dwarf galaxies that are these leftover remnants from the era of the very first galaxies. So if you remember this picture from earlier, just a few minutes ago, you formed these first galaxies early on, but then the very smallest ones ended up being kind of fried by reionization. They were quenched following reionization and were unable to continue forming stars. And so you had these small systems that were large enough to start forming stars early on, but then ever since reionization have just kind of been hanging around and maybe merging into other galaxies, or in the case of Reticulum 2, end up surviving till present day, orbiting around something else. So these are really ancient systems that are these windows into the past. And just to kind of show also, so this is just a little visualization of two galaxies merging, and you can see here how the smaller the galaxy is almost always very thoroughly ripped apart, and the stars from that galaxy end up all over. But in particular, you can see there's stars here in the center, but there's also a high density of other stars. So a lot of times people like to look into the stellar halo for some of these very older accreted stars. So that's something else to look for as well. Oh, and I wanted to show this because I thought this was very fun. This was a little cartoon that I collaborated on with a UMass student, Ginny O'Grady, who's a student here in Boston, who's now graduated. But she did a little cartoon about galactic archaeology. And so this is one little portion of it. But just to explain galactic archaeology and the goal of it. So galactic archaeology, archaeologists like myself and my collaborators, we study the history of the Milky Way galaxy by observing the old stars we can find today. So the old stars are fossils. You see this very cute little old star fossil. And my research is in trying to understand like the small galaxies and these relics from the first small galaxies that merged in order to create the Milky Way. So these ultra-faint dwarf galaxies like Reticulum 2 and others. The way that we do this is by using galaxy simulations to learn and help interpret observations about the galaxy today, to learn about the past. This is one galaxy simulation that we have worked on. These are the caterpillar simulations, and what you're seeing here is a Milky Way mass galaxy forming here in the center. And then over time, it is accreting a bunch of smaller systems, get bigger and bigger, until we're going to reach present day, and you have a Milky Way mass system, still with quite a bunch of other little galaxies and other little halos around it. And this is just like one simulation, but of course we want to compare that to real information. And so these are, some of the small halos you see in the caterpillar simulations, these are some of the halos. Then you can go and look for the actual dwarf galaxies around us in the Milky Way today. And of course, the Melpor stars as well, that are often stripped from some of these very old ancient systems. So now to finally get into the nuclear part of this for the JINA talk here. One of the most interesting things about these really ancient stars is the stellar chemical abundances of these stars. So when a star is formed, like let's say 13 billion years ago, we have some early gas cloud in one of these really ancient old systems. And that gas collapses and it forms some stars. And if those stars aren't too massive, let's say they're below solar mass, they can survive to present day. And then we will be able to find them potentially in these small ancient systems around us or in the halo. And by looking at the chemical abundances using spectra, we have windows into the chemical elements that existed 13 billion years ago. So this is what we can see today, and we can look in the past and learn all about these early systems and start trying to interpret how they formed. And then also something I'm interested in from the galaxy formation side is start trying to interpret like their origins in the galaxies as well, and how we can learn about the galaxy formation processes in addition to the nucleosynthetic sources that formed all of this. And one more little cartoon picture. So you can see here the galactic archaeologist is finding and classifying this old fossil little star by looking at its spectra and learning about the stellar chemical abundances of this little old star. So the stellar chemical abundances of the old stars and some of these really old small galaxies, they contain information about early galaxy formation and early chemical enrichment, which are things we're very interested in. But it's obviously very complex, and there's a lot of structure in the observations that we don't yet understand. So it's already been shown like several times that stellar chemical abundances are a promising method to help identify and study ancient stars from these ancient dwarf galaxies. But the current simulations that exist, just due to computational limitations and limitations around the modeling, often can't explain or have not been able to yet explain the scatter in the full distributions of the observations that we're getting now, and the star-by-star distributions of these observed chemical abundances. So we're now getting good enough on the observation side, getting tons of high-resolution spectra, but simulations are still making a lot of simplifying assumptions of this homogeneous mixing, or not being able to resolve fully. Like there's a large variety of scale between the full galaxy and individual like star formation. And so you'll frequently have one particle that represents hundreds, and some of the larger simulations, thousands of stars. And so you're lacking a lot of the precision and like the enrichment and the feedback from these individual stars themselves. So if we want to fully take advantage of all the data that exists, if we want to fully start to interpret what we're seeing and learn about these early epochs of galaxy formation, chemical enrichment, we need some high resolution simulations with like better resolution of stars and more detailed stellar chemical abundances, more of a focus on that, which has not been done historically. This is the time to do it, particularly because I just mentioned we're so much high resolution spectra that's both currently being obtained and forthcoming and already exists. So there's already spectra for thousands of stars, and there's much more to come. There's a bunch of surveys, so it's a great time to be interested in spectroscopy. But then we need to make sure that we are also prepared on the theory side, where we actually are having full distributions and not just capturing mean trends, but we're actually having full, scatter and distributions and things like that. So this has been the new frontier that was needed on the theory side. High-resolution galaxy simulations with detailed chemical abundances in individual stars. So that was the motivation. And for the first time, this was not crazy. In the last several years, galaxy simulations are now starting to be able to reach 1 parsec gas resolution and single star particle resolution. So you're not needing to have one particle represent hundreds of stars. You can have single stars and the feedbacks from trace from that star. And all this is orders of magnitude better than previous years and is needed now to interpret the detailed distributions of chemical abundance data that's being obtained. So this was the motivation for us. So we are one of the people working on a star-by-star model. In the last 4 years, a few groups have started doing this. And just to kind of give a brief understanding of what a star-by-star model is in a galaxy simulation. So historically, you would maybe just have one of these blue particles here. We'll call that a star particle that kind of was an aggregate that you kind of paste distribution of star masses on and have some feedback coming off of that. But it's all kind of just collected in one particle. Now we're able to define some mass resolution below which you still have to aggregate into a single particle. So we can't have absolutely every star as its own particle. That's still both beyond computational abilities and unnecessary for the questions that we're asking. But for all the stars that have feedback and enrichment that we care about on the timescales of the simulations, we can have them be traced as their own individual particle. So something like this here, you can assign some resolution. And so you have either more star particles, fewer aggregate particles, more individual particles, and so on. And then this allows us to directly model feedback, so such as from like winds, supernova, things like that, and also individually track enrichment from the yields of individual stars and how those mix into the gas and end up collapsing into new stars and things like that. So it's a lot more detail than older simulations. So this was what we did with the Aeos simulations. So the Aeos simulations have, right now, it is a box of about 90 like very small star-forming galaxies, about a megaparsec. But what is new and interesting about these simulations is we have a very detailed treatment of stellar yields. So these new carefully selected yields. We have metal mixing from individual stars. We trace 10 different metals and then additional like things about where they came from. Like, did they come from POP3? Did they come from AGB winds? Different, like where exactly the metal came from. And then we have, as I've mentioned, the star-by-star model. So we are able to directly have feedback in metal enrichment from individual stars. In our case, everything greater than 2 solar masses. And we have this focus that we are very interested in, like studying some of these very early small galaxies, and then also looking at the ones that will survive to present day so that we can directly compare to the observations around the Milky Way. Oh, and yeah, just to explain the name really quick. So Aeos is one of the horses that pulls Helios, the sun god, across the sky in Greek mythology. It was also an acronym at one point, but that has been lost to time, which is probably for the best. But yeah, so this is, Aeos is the horse, one of the horses that pulls the sun across the sky. Just to very briefly go over some of the logistics of this simulation, it was run with a modified version of ENSO. So ENSO is a hydrodynamic astrophysical simulation code. And we modified it to include the star-by-star model and the additional yields and feedback models so that we could have this higher level of detail. And so that's the base code that we are running is with ENSO. The fiducial cosmological simulation that we have been analyzing right now is a 1 megaparsec box with gas resolution of 1 parsec and an individual particle for every star greater than 2 solar masses, which ends up being about 200,000 particles of that order. We also, something that is somewhat unique to Aeos, because we not all of the other star-by-star models include this, is that we have POP3 stars and enrichment from POP3 stars as well. So it's not just POP2. With this is very computationally intensive, as you might imagine. So it's right now focusing on the very early, just the first few hundred mega years after the Big Bang, which is also a period of time we're very interested in seeing how some of these first halos get enriched and some of the first formation processes and things like that. So right now we've been looking at the first few hundred mega years while also preparing some zooms that will run farther for the direct comparison with observations. Already, though, with the simulation, this one simulation, we have about 100 star-forming halos that we're able to look at. And we trace in great detail 10 metals from different nucleosynthetic sources. From core collapse supernova, AGB, type 1a, both POP3 and POP2. We also have some additional metal tracer fields that I've mentioned, including an R process field, so we can look at some enrichment from that. So there's 20 total tracers that we look at for both every star and every gas cell. And then after about 300 mega years, this is how the box looks. We're very zoomed out here, but you can see here this is the gas density. And I've circled in red every one of the 91 star-forming halos, all these very tiny galaxies. And these are just some of the metals that we see here that we're able to look at. So we have right here just iron, nitrogen, oxygen, and there are more as well. Plus an R process field, and plus these additional tracers of where these metals came from. And so all of these very small circled galaxies here, they are several dozen of them are these very extremely high redshift galaxies. As I said, we're looking at just right now the first 300 mega years of the universe. And so you can see here, I've plotted their stellar mass and their halo mass, and also here kind of simplified this plot here to show it on the right as just a stellar mass halo mass relation for this very small section of the early universe that we've simulated. I also should point out that we have, so there's 2 Aeos simulations at the moment, Aeos 10 and Aeos 20. I'll discuss more about them later, but they differ only in their handling of POP3, since that's very uncertain. And then also we have some comparison simulations that we ran. So we ran 7 simulations without this star-by-star model to see how much the properties changed of the, like how important this is and when it's necessary to do star-by-star versus when it's not. But all of these you can see are pretty small galaxies overall. Our largest one is about a stellar mass of 10 to the 7. And there's many below about 100 solar masses. These are very small. So looking first, just I'll briefly say about the comparison simulations. The main takeaway from this is that the bulk properties of the simulation volume, such as the total star formation and a lot of the bulk properties of the halos, those are not significantly affected by having star-by-star or not having star-by-star feedback and enrichment. There are some differences here. You can see, like, it looks like maybe in this, the POP2 star formation started a little bit earlier on the comparison simulations, but there's quite a bit of stochasticity just even within these simulations themselves. And so there's nothing very significant about the bulk properties that was changed by this inclusion of the very detailed model. It really depends on what questions you're asking, but for the bulk properties, that's not necessary to do this level of detail. The things where it is necessary to do this level of detail are some of these selected results that I would like to walk through, including particularly how to get these detailed stellar chemical abundances, which was our main goal. So I'm just going to walk through 3 selected results from these first simulations that we are preparing to publish right now, because these are some of the ones I'm personally most interested in, but there's a lot of different directions people are going with these simulations. So I'm really curious if anyone has any thoughts in general about like applications or things that would be interesting to look at in these, really detailed beginning of the universe simulations. But first, looking at the chemical abundances of stars. So we saw, this is not a completely new idea, and this was actually one of the goals of the simulation, was to look at how the chemical abundances of the stars themselves could be used to learn more about their origins in different galaxies. And so that is something that we were hoping to see, and something that we did see when we ended up running the simulations. And so I'm going to walk through a little proof of concept of this and what I'm talking about. This is one video from very early in the universe here at redshift 15. And this is something that we would never be able to see in real life. Of course, this is something you can only see in a simulation, is this like little video of something that would happen in the far past. We have 3 different galaxies here. And I've started showing when they start forming POP2 here. It's progenitors 1, 2, and 3, and they're colored according to blue, purple, and green. And what's happening here is they're kind of circling around. They each start forming their own stars individually, and then they end up merging, and the merged galaxy continues to form stars, and that's shown in orange. So because of simulation, we can go and we can look at exactly how this galaxy formed and where all these stars came from. But that's not something, of course, we could do in real life. Something in real life that if this galaxy were to survive and end up near the Milky Way, the sort of thing we'd actually be able to observe in real data is what I'm now showing, which is stellar chemical abundances of the stars that would survive to present day. And they're once again colored by their origins. And in this case, the size of the dot is how many stars are in that bin, which is binned according to the like kind of expected observational uncertainties of these stars if they were in the stellar halo. And the point I want to just make with this is that if you look at this, you can see structure in the diagram. You can see in this slice of chemical abundance space, there's like different areas that are occupied by different groups of stars. And then if you know the colors, if you know the origins of these stars, you see that those different groups tend to correspond to where those stars formed in their different progenitor galaxies. So this is very similar to an idea called chemical tagging. And if you're not familiar with chemical tagging, it is this idea of looking at spectra of stars and using that to relate back to their birth cluster where they were born. Because, as I'd mentioned before, they're kind of like windows into the gas cloud that form these stars. So it's not unexpected necessarily to see this, but it's very interesting. And then we're not just measuring like nitrogen and iron. We have a lot of different metals. And so it's a multi-dimensional space, this chemical abundance space. So there's a lot of structure within it, even in this very simple example of these three little galaxies merging. Also, because an additional thing I'd like to point out is that even within some of these, like within the same colors, there is definitely scatter. They're not all in the exact same. Even though they formed in the same place, they don't have all the exact same stellar chemical abundances. There's scatter due to like the different like timing of different nucleosynthetic sources, the mixing within the gas. This is especially prevalent with some of these, like so strontium, which is very little. As soon as some of it forms, and you can get these spreads in these like very like small gas clouds and things like that. And so there's a lot of structure and a lot of scatter. And so we also see a lot of scatter within real data. And so what we're really interested in as some of our next steps is to untangle how much observed scatter we expect to originate from like galaxy mergers. So these kind of like, hierarchical galaxy processes causing these different areas of the chemical abundance space to be occupied, versus how much of it is different nucleosynthetic sources that are even within galaxies causing a lot of scatter and a lot of structure. So that is something that we are already seeing and will continue to be looking into and ultimately comparing to the real stars around us today. But now to go on to the next selected result. So very early in the universe, the galaxies live in these very small dark matter halos compared to the dark matter halos that exist today. They're much smaller, and so they have much smaller potentials. And so this makes it very difficult for them to hold on to their gas and metals. So as soon as there's any sort of feedback, say a supernova goes off, they can just blow out their gas and their metals, and it can end up all over the place in the galaxies around them. And so these early galaxies, anytime they're in like a somewhat clustered environment, we're seeing them very frequently share their gas and metals. And in fact, this has been leading to some examples of external enrichment, which we were interested to see, which are galaxies that started their star formation with POP2 and fully skipped past POP3. And so I'm going to show here some area. This is an area of the simulation where in the center here we have a large, more evolved halo that has been forming stars since before 150 mega years after the Big Bang. And so it started star formation pretty early, And you can see here, so this in blue is the POP3. So it starts forming POP3, eventually gets enough metals, it starts POP2, and then it kind of takes off. So this galaxy has been evolving for, over 100 mega years. But it's in an environment, you can see here, there are several other little galaxies around it. And even though this one is bigger, it still doesn't have that big of a potential. And so it's been throwing out a lot of these metals that were formed from these like POP3 core collapse supernova. And these two galaxies on the side both became enriched significantly in metals from this middle one. And so I'm showing here just one of the halos here. Its star formation started obviously later than the central one, but when it started, it already had enough metals to just immediately start with POP2, which is interesting around the same time also that the middle one had enough metals to start with POP2. So it's, I've been struggling a little bit to think about how I want to think about this exactly, because I've been starting to think about, they're not really individuals, right? It's more of a system, especially in these really early groups of galaxies. Because as I've said, these early small galaxies have very small potentials. Their gas and their metals are all over the place, and there's this time scale for them getting them back. But in the interim, they get, collected in lots of other galaxies around them. And so the galaxies in these cluster environments freely share their gas and function like a larger system rather than individual galaxies, which is not how they're normally analyzed in galaxy simulations. They're usually treated as individuals. So I think it's interesting to maybe think of these more of this more cohesive system of individuals working and sharing stars and gas and all of this together. So that's been something we've been seeing a lot of in the early, a lot of the sharing of gas in this very first several hundred mega years. So in addition to that, I wanted to very briefly talk about POP3, because this was something that was and is very uncertain, and was something that we spent a while looking at and testing different things. And what we found is that, first of all, the small galaxies are significantly affected by the choice of the POP3 initial mass function. And that's because they are very affected by increased amounts of ionizing radiation. And when you have different POP3 initial mass functions, you can have more massive POP3 stars with more radiation that suppresses these galaxies. So just to briefly show this, due to the high uncertainty of the POP3 initial mass function, which is the distribution of masses we expect POP3 to have from, characteristic mass of 10 or 20 solar masses up to 100 or more solar masses. So these very massive early stars. Due to the high uncertainty of what that distribution is, we ran simulations with different POP3 characteristic masses for the mass function. And so we called these Aeos 10 and Aeos 20, where, so this characteristic mass here is below there's an exponential suppression. And so you end up having more massive stars, POP3 stars in this Aeos 20 compared to the Aeos 10 has a little bit less massive POP3 stars on average. And just this change resulted in a very significant difference in the ionization of the simulation volume. And that's what I'm showing here, is over time, watching as after the first stars start forming, how quickly the whole volume gets ionized. And so Aeos 10 never gets very ionized. And so this was the one we've been using for our fiducial model, because this is more and with expectations around the timelines for ionization in the universe. And we also, the comparison simulations also used this Aeos 10, this 10 solar mass characteristic mass. So we showed those as well. And in all those cases, there is stochasticity, but in all those cases, the ionization is much lower than the Aeos 20, which ionizes much faster than expected. And this high ionization of the volume ends up suppressing the formation of the smallest galaxies. So this is a histogram showing the number of different mass galaxies in the different simulations. And on the little bit of the higher mass, asterisk on higher mass here, they're all still pretty small. But on the higher mass end here, they exist in both Aeos 10 and Aeos 20. We have some blue and some red. But on this low mass end, there's a lot of very small, under 100 solar masses, like these little halos that just started forming little bits of stars in Aeos 10. But we don't see that in Aeos 20. That is suppressed significantly by like almost an order of magnitude. It's much lower. And so we were seeing that this very noticeable difference in ionization was also leading to differences in the distribution of galaxies that exist and like how easy it is to make these tiny little star-forming halos. So that was something that we've been looking at as well. And we are very hesitant to say anything more than that in terms of actually constraining anything about the POP3 IMF, because our simulation volume is not representative of the entire universe. And so even though this ionization amount is much higher than we would expect, there's definitely more work to be done before we can say more about like what is actually realistic for the POP3 initial mass function and how that leads to the ionization of different volumes in different areas of the universe and things like that. But it was something that we wanted to point out, especially for other simulators, because this was very significant in affecting our ionization and our galaxy formation. And then here in just the last bit of time, I wanted to plug also some additional bonus work that my RU student did over the summer, which was very interesting, and I thought would be interesting to the nuclear astrophysics group, which was about neutron star mergers in dwarf galaxies and how likely they are to be a source of the heavy metal R process enrichment. So just to kind of very briefly step through this, the heavy elements from the rapid neutron capture process, the R process, have been observed in tiny dwarf galaxies like Reticulum-2, which I showed a picture of earlier. And this has historically been assumed to be a result of neutron star mergers. So this was confirmed with GW 1708-17 that neutron star mergers can make these heavy elements with this rapid neutron capture process. And so, this has been the only confirmed site so far. But there are a lot of questions around if it could actually be the source, especially in these really small and early galaxies. And two of the issues around that are that, well, first, neutron star binaries, which you need for the merger, they're formed by supernova. And so supernova can give them a little kick, little velocity when they form because of the asymmetries in the explosion. So this is called a natal kick. And then it takes time both to form and merge them. So if you have a little neutron star binary in a small galaxy and it starts moving and it takes a while to form, I was just been talking about how these potentials are very low. Like you can just fly out of a small galaxy. And so then how would you get this enrichment that you're seeing? So this is something that we were looking at with this this little analytic model that we post-processed on some simulations that I had been working on, where we assumed that we assumed that when a binary would form, that it would have, we took some different distributions of natal kick and delay time. And then if the explosion occurred, the merger occurred like near the center of the galaxy, we get R2, which is extremely enriched. If it exploded farther out, kind of like at or beyond, slightly beyond the virial radius, we'd get some R1. But then sometimes it would just fly all the way out, very far away, and then we would have no enrichment whatsoever. And then we were comparing to the actual faint dwarf galaxies that we see around the Milky Way today to see if we could reproduce kind of the fraction of these different amounts of enrichment. Just to jump straight to the result, because this is just a little teaser, we are able to reproduce the fraction of enrichment that we see with a variety of choices for the delay time, so that's this T-min, this alpha, and also the natal kicks, which is this kind of sigma as a Maxwellian distribution. And also some of the cutoffs for how far away it needs to, we vary that as well to get different amounts of enrichment. So we are able to reproduce, but we are not able to reproduce observations with what are currently considered like some of the best choice literature values for these different distributions. There's still a lot of debate and questions around the delay time and around the natal kicks. So there's quite a bit more work to do both on that and within our own models. But this initial result was implying that either neutron star mergers are not actually favored as the primary source in these really small dwarf galaxies early on, or that we need some sort of different natal kick and delay time distributions than what is currently considered the most recent to date literature estimates. So we'll definitely be looking more at that as well. And Christine will be at AAS as well, presenting this. So I'll just show now the conclusions here. To reiterate, these are some of the selected results from the first Aeos simulations, which are star-by-star cosmological galaxy simulations with 10 different metals, 10 different additional tracer fields, POP3 enrichment, metal mixing, and more. And already we're seeing that we are able to look at the origins of galaxies and also see scatter within galaxies. We're seeing how these galaxies interact with each other and how they can externally enrich, and some of them start with POP2. And then we're also seeing how important the choice of POP3 enrichment and POP3 mass function is when looking at these very early times and looking at these very small early galaxies. So thank you. I would love to take some questions.
Thank you, Kaley, for the wonderful talk. That's really some exciting results.